This is part 3 of 4 chemical reactions video experiments. In this video, we will be studying precipitation reactions, which are an example of double displacement reactions. So the fourth type of chemical reaction is precipitation or double displacement, but we have to lay a little groundwork before we get there, and that's the solubility precipitation concept. Ionic compounds, that is, salts, are held together by strong electrostatic forces of attraction of oppositely charged ions. And that's what ionic bonds are, the attraction between cations and anions. So look at the formation of potassium chloride, ionic salt. Potassium metal is a reactive group 1A metal with one valence electron it wants to lose. And chlorine is a reactive 7A nonmetal that needs one electron to complete its octet. So they react, potassium giving its electron to chloride, forming potassium ions and chloride anions. We have a potassium chloride salt. Now the strength of these bonds results in a high melting point of ionic compounds, typically greater than 400 degrees C. In fact, in the case of potassium chloride, has a melting point of 772 degrees C and a boiling point of 1411 degrees C. That's a lot of heat required to separate these ions. They're strongly attracted. Amazingly, many ionic compounds are soluble in water at room temperature without heating. So here's potassium chloride salt. Put it in water at room temperature. The ions are separated into potassium cations and chloride anions. How does that happen? Well, when ionic compounds dissolve in water, their cations and anions are separated and they disperse in water, forming a solution at room temperature without heating. Take a look at this illustration. Here we have potassium chloride solid, solute. We put it in water, and then this represents what's happening in solution. The small, highly polar water molecules, here they are, they insert themselves between the positive and negative ions of this solute, separating the ions. The slightly negative or partial negative oxygen atoms move close to the solute cation, in this case potassium. They surround it. At the same time, the slightly positive or partially positive hydrogen atoms of the water molecule surround and move close to the anion, in this case chloride. In this way, water molecules effectively insulate the solute ions from each other, thereby making it easier for the solute to pass from the solid state into solution, that is, easier to dissolve. So continuing with the solubility precipitation concept, the process of a salt dissolving in water is shown by the following chemical equation. Here's potassium chloride solid, salt in water, separates into potassium cations and chloride anions, and the suffix aq means aqueous or dissolved in water. The solubility of ionic compounds as well as polar compounds is commonly described by the rule like dissolves like. Ions contain positive and negative charges, and water contains partial positive and negative charges, and in that sense, although they're not identical, they are alike. Now, while it's true that many ionic compounds are water soluble, some ionic compounds are actually insoluble because the force of ionic attraction between cations and anions of the salt are stronger than the attraction between water and the ions of the salt. And one example we're going to look at is that of a water-insoluble ionic salt called lithium fluoride. The solubility of lithium fluoride in water is only 0.27 grams per 100 mils. It's quite insoluble. Let's consider what happens when an aqueous solution of lithium iodide is mixed with an aqueous solution of potassium fluoride. So here I'm dissolving lithium iodide in water. Notice the solubility is very high, 151 grams per 100 mils of solution. That's a lot of lithium iodide. So it produces a clear colorless solution containing lithium ions and iodide anions. We can also make a solution of potassium fluoride, dissolving it in water. Notice the solubility is also very high, 92 grams of potassium fluoride per 100 ml of solution. So we get another clear, colorless solution containing potassium ions and fluoride ions. But what would happen if we mix these two solutions together? Well, the potassium ions would come in contact with the iodide ions, but they are very soluble, 148 grams per 100 ml of solution. But notice that lithium fluoride is not so soluble. When a lithium cation collides with a fluoride anion, they will combine together so strongly that water can't separate them, and they will immediately precipitate as a solid, lithium fluoride. Its solubility is approximately 0.3 grams per 100 ml of solution. And lithium fluoride is thus a precipitate. Potassium and iodine ions remain in solution, and they are spectator ions. And this is a precipitation reaction. So looking further at this reaction, potassium fluoride reacting with lithium iodide precipitates lithium fluoride solid, and potassium iodide aqueous remains in solution. This is called the reaction equation. Let's take another look at it. Here is a clear colorless solution of lithium iodide, and in it I'm going to add a clear colorless solution of potassium fluoride. The solid that's coming out of solution is insoluble, or at least lithium fluoride of low solubility. Potassium iodide remains in solution. So if we take our reaction equation and break it apart, everywhere we have the suffix AQ, it really means that the salt is present as ions. So KFAQ on the left side is really potassium ions and fluoride ions, and lithium iodide AQ is really lithium ions and iodide ions. On the right side of the equation we have lithium fluoride solid. Well, that can't be broken apart into ions because it isn't present as ions, it's a solid. But we do have potassium iodide AQ, which I can break apart into potassium ions and iodide anions. This big messy equation is called the ionic equation. If we leave out the spectator ions, the ones that don't react, and include only the ones that do react, we get a much tidier equation called the net ionic equation. So I've left out potassium ions and iodide ions on both sides since they're not really reacting, and I only include lithium and fluoride on the left and lithium fluoride on the right. The net ionic equation leaves out spectator ions and shows only the ions that react to form a precipitate. Solubility rules for precipitation reactions. Now it turns out that many ionic compounds are soluble in water, but then some are insoluble. In precipitation reactions, two aqueous solutions react to form a compound that is not soluble in water, and that is, it's a precipitate. We need a method of predicting when precipitates will form. Now the solubility of most inorganic compounds has been tested, and solubility patterns have been observed and are summarized in the following table. Now the solubility rules are not without exception, but they do hold in most cases. So first of all, we're going to list ions that are almost always soluble. For example, the group 1A ions, hydrogen through francium, and ammonium ion. They're virtually all soluble. Nitrate, perchlorate, chlorate, and acetate, all of these compounds made from these ions are typically always soluble. Exception, as we've just seen, is lithium fluoride. Lithium's a group 1A ion. Chlorides, bromides, and iodides, almost all their salts are soluble unless they're combined with lead-2, mercury-1, mercury-2, silver, in which case the halides are insoluble. Almost all sulfates are soluble unless the sulfate is combined with lead-2, mercury-1, mercury-2, silver, calcium, strontium, or barium, in which case they're insoluble, otherwise sulfates are soluble. And finally, virtually all fluorides are soluble unless they're combined with lead-2, mercury-1, mercury-2, or the group 2A ions, beryllium through radium, and of course lithium, which is a rare exception that we spoke of earlier. So those are the ions that are virtually always insoluble compounds. Now, what follows is a list of a couple groups of ions that are almost always insoluble. So almost all hydroxide compounds are insoluble unless the hydroxide is combined with ammonium or the group 1A ions or barium, in which case the hydroxides happen to be soluble. And finally, all chromates, all phosphates, all carbonates, sulfides, and sulfites, they're all insoluble in any of their compounds unless they happen to be combined with ammonium or the group 1A ions, in which case they're soluble. And we define solubility in this way. Less than 1 gram per liter is considered insoluble. Slightly soluble is 1 to 10 grams per liter, and soluble is less than 10 grams per liter. Solubility rules for precipitation reactions. Let's get some practice. So for each of the following compounds, I'd like you to predict whether they are soluble or insoluble. And you can use the symbol AQ, meaning soluble, or S for insoluble or solid. First of all, potassium nitrate. We've just seen that all nitrates and all group 1A ions, of which potassium is a member, are soluble, so certainly potassium nitrate would be a soluble compound. How about sodium carbonate, Na2CO3? Well, it's true that most carbonates are insoluble, but when combined with the group 1A ions, like sodium for example, they're soluble. Ammonium phosphate. We saw that all phosphates are insoluble unless they're combined with one of these exceptions, and ammonium is one of those exceptions, and so ammonium phosphate is also soluble. How about calcium carbonate, CaCO3? We've seen that almost all carbonates are insoluble, and the only case where it's not is when the carbonate is combined with ammonium or the group 1A ions. Well, calcium is not one of those exceptions, and therefore calcium carbonate is in fact insoluble. Calcium carbonate is limestone. It's not soluble. Try the next group, magnesium sulfate. Well, we've seen that all sulfates are soluble unless they're combined with lead, 2, mercury, silver, calcium, strontium, or barium, in which case they're insoluble. Well, magnesium is not one of these exceptions, and so magnesium sulfate would in fact be soluble. How about aluminum hydroxide? You see from the table that all hydroxides are insoluble unless they're combined with ammonium, barium, or group 1A ions. Well, aluminum is not one of those exceptions, and therefore aluminum hydroxide will in fact be insoluble. How about iron 3 chloride? Well, we saw up here that all chlorides are soluble unless they're combined with lead, 2, mercury 1, mercury 2, or silver. Now, iron is not in that list, and therefore iron 3 chloride must be soluble. And finally, how about barium sulfate? We saw that all sulfates are soluble unless they're combined with lead, mercury, silver, calcium, strontium, or barium. Well, it turns out that barium is one of the exceptions. Barium sulfate happens to be insoluble. Okay, let's get some practice. Let's combine aqueous silver nitrate with aqueous sodium chloride. Both of these are soluble. Let's interchange ions. The brown line connects the inner ions, so when sodium ion meets nitrate ion, well, we know that from group solubility rule number 1 that all nitrates are soluble and all sodium salts, group 1A ions, are soluble, so certainly silver nitrate is soluble. But what about silver meeting chloride? Well, rule number 2 tells us that all chlorides are soluble unless chloride is combined with lead, 2, mercury 1, mercury 2, or silver. So there it is. Silver chloride happens to be insoluble. So we can write the products NaNO3 aqueous and silver chloride solid precipitate. Now it turns out that this equation is balanced because all of the ions have a charge of magnitude 1. So both silver and sodium have a +1 charge, and nitrate and chloride have a -1 charge. The next step is to eliminate the spectator ions. That would be nitrate and sodium, and that leaves the net ionic equation of silver ion plus chloride ion makes silver chloride solid precipitate. So in the test tube, I have a clear colorless solution of silver nitrate, and I'm adding a clear colorless solution of sodium chloride. And when they mix, we see the immediate formation of a dense white precipitate, and that would be silver chloride. Let's try one more. Iron 3 chloride aqueous combined with sodium hydroxide aqueous. Let's exchange ions. The inner brown line connects sodium and chloride, and we know that sodium chloride is soluble. What about iron 3 ion and hydroxide ion? Well, rule number 5 tells us that all hydroxides are insoluble unless hydroxide is combined with ammonium, barium, or group 1A ions. Well, iron 3 is not one of those exceptions, and so iron 3 hydroxide is indeed insoluble. So we can write for products sodium chloride and iron 3 hydroxide solid. Now this equation is not balanced. I can see 3 hydroxides on the right and only 1 on the left, and I can see 3 chlorides on the left and only 1 on the right. So if we put 3 NaCl and 3 NaOH, we will balance the equation. Let's now eliminate the spectator ions, sodium and chloride, and that would give us the net ionic equation of iron 3 ion combining with 3 hydroxide ions to give us FeOH3 times, and that's insoluble precipitate. In the test tube, I have a clear yellow solution of iron 3 chloride, and in the pipette I am adding clear sodium hydroxide solution, and when they meet, we see the formation of an orange-brown precipitate of iron 3 hydroxide, which in fact is an aqueous form of rust. A little more practice. Potassium iodide plus lead-2 nitrate. Let's interchange ions. The outer blue line shows the association of potassium and nitrate ions, and we know that the group 1A ion potassium and nitrate ions are all soluble, so potassium nitrate will be soluble. But what about lead-2 ion and iodide? Well, rule number 2 tells us that all iodides are soluble unless iodide is combined with, well, there it is, lead-2. So lead-2 iodide is insoluble. So we can write for products potassium nitrate aqueous and lead-2 iodide solid precipitate. Now this reaction is not balanced. As you can see, I have 2 iodides on the right and 1 on the left. I have 2 nitrates on the left and 1 on the right, so we should double up on the potassium iodide and the potassium nitrate, and now it's balanced. Let's eliminate the spectator ions of potassium and nitrate, leaving us with the net ionic equation of iodide plus lead-2 ion makes lead-2 iodide solid precipitate. In the test tube, I have a colorless solution of potassium iodide, and in the pipette, I have a clear colorless solution of lead-2 nitrate. And when they combine, you see the brilliant yellow color of lead-2 iodide precipitate. Last one. Here's sodium chromate aqueous solution and silver nitrate aqueous solution. Let's interchange ions. We know that the outer ions, sodium and nitrate, form a soluble salt, but what about silver and chromate? Well, rule number 6 tells us that all chromates are insoluble unless combined with group 1A or ammonium ions, and silver is not one of those exceptions, and so silver chromate is in fact insoluble. We can write for products sodium nitrate aqueous and silver chromate solid precipitate. Let's balance the equation. I see 2 silvers on the right, but only 1 on the left. And I see 2 sodiums on the left and 1 on the right. So if we double up on the silver nitrate and double up on the sodium nitrate, that's balanced. Now let's eliminate the spectator ions, sodium and nitrate, leaving us with the net ionic equation. Chromate ion plus silver ion makes silver chromate solid precipitate. So in the test tube I have a clear yellow solution of sodium chromate, and from the pipette I'm going to deliver a clear colorless solution of silver nitrate, and when the two meet forms a brilliant brick red colored precipitate of silver chromate. So this is the end of part 3 of the 4 chemical reactions video experiments. You'll need to see the written lab procedure for additional content that is not in this video, and for the lab report requirements, including equations you need to balance and some questions to answer. There are a few short video clips related to precipitation reactions that you should also watch. These videos and/or their hyperlinks are posted on Blackboard. Thanks for watching.